and welcome to the class webinar. Throughout the webinar, all participants will be in a listen-only mode, and afterwards there will be question and answers, followed by an online polling session. Just to remind you, this webinar is being recorded, and today I am pleased to present Simon Brooke. Please begin your meeting.
Thank you, and good afternoon everyone, and welcome to the third class webinar as part of our dissemination events for the class project. Today we are going to have a brief recap on the class project and a description of the highlights of where we're up to as the part of the delivery of the class project. We have a colleague, David Wagstaff from National Grid, who will talk about the ICCP interface and their activities under the class project. And then I'll be joined by Paul Turner from Electricity Northwest, who will give us a fairly good overview of the class trials, and in particular talk through some of the results that we've got associated with live frequency events. And then we run into a question and answer session. Okay, just so you know what the format of today is, we'll have about 30 minutes of presentations followed by a question and answer session. You'll have opportunity throughout the webinar to submit written questions online through your PC, or you can dial in to listen and take part in the live question and answers at the end. So you've got two ways to be able to submit questions. Depending on the responses that we get, we will switch between the two. We will take live questions, or we may at some point move to the written questions online. Just depends how many we get and what the timing is. Okay, so just to recap for everyone, we have all the DNOs have moved from a world of fit and forget, where we're operating very passive networks. We're moving now into more active networks. And we based our innovation strategy around trying to maximise the use of the existing assets that we have, those assets that have already been paid for by our customers. And what we try and do, or what we're trying to do as part of the innovation strategy, is prove that technology which is deployable today and actually deliver some real innovative solutions to the problems that we have, to underpin what we're trying to do, which is deliver value to our customers. We want to be able to offer new services and give our customers much greater choice in the future. Okay, now we've been very fortunate as part of the Low Carbon Network Fund to have been successful in receiving funding for 4 flagship projects. Class, which we'll be talking about today, capacity to customers, which comes to an end very soon, Smart Street, and unfortunately our presentation material has not worked very well, and it should actually, with the space that you see, should say Respond, which was the Tier 2 project that we won last year. And they are all designed to deliver maximum value from the current assets that we have and give customers choice. So in both Class, capacity to customers, and Smart Street, we are looking at demand response tied in with active network management solutions. And under the Respond project, we'll be looking for a fault current limiting service provided by our customers to help us manage fault levels on our network. Okay, so just as a reminder of what the Class project is all about, Class is to try and demonstrate the relationship between voltage and demand. We all know that if you are able to vary the voltage, you are able to vary demand. What we don't know is by how much. So there is some quite extensive trials to actually work out when we reduce the voltage at any particular time of the day, what relationship do we have? So what does the demand move by? And the reason why we want to know that is because we want to be able to change the voltage at the time of system peak to be able to defer the need for reinforcement, effectively buy ourselves a window of opportunity. So just let me recap on where we are up to date with the project. We started the project in January 2013. The first thing we did was do all the site selections for all the substations that we were going to involve in the class trials, and there were 60 primaries. We then installed all the hardware in those substations, and we delivered the ICCP link between ourselves and National Grid, which effectively formed the first real-time data link between National Grid and any other DNO to be able to send data and commands across. We spent quite a bit of time then designing the trials and the test regimes that will help us provide all the information and data so we could work out what the voltage and demand relationship was. And in parallel with that, we worked out how we would survey our customers to be able to ascertain whether the customers noticed any of the voltage changes that we were going to do as part of the trials. Now, we're at that point where the trials are ongoing, but at this time today, what we're going to do is provide a bit of information on where the trials are and some of the early results. Okay, I'll now hand over to David Wagstaff from National Grid, who will talk about the ICCP link.
Good afternoon, my name's Dave Wagstaff, and I'd like to talk to you about the ICCP link between National Grid and Electricity North West. If I can just set the scene slightly at the start, previously we had an electrical boundary between the transmission and distribution networks, and neither party could see beyond their part of the boundary. Although that boundary still exists, we can now, using the ICCP link, both see beyond our own boundary, and this is something that can be quite important to us for the future. Now, if I explain what an ICCP link is, it's a secure industry standard protocol between two parties. This one is a direct fibre optic connection, and it allows us to exchange data between our management system and Electricity North West management system. The results we've had out from the class project and this link is that we've had very good results. The main thing is we've had no abnormal results from the class trials, so we were expecting it to work, and the thing is we've had no operational impacts, which is what we wanted. The ICCP link has been proved to be secure and robust. It's also the very first of its kind. We've had improved visibility of the information either side of the boundary, and this is quite important for us going forward into the future. One of the extra things we tested was the ability to send control options for both frequency and demand over this link, and that's an improvement over the current system. If I can just take you through some of the learning points we've found. Although everything has worked as we wanted it to work and worked as we planned for it to work, there were a few things that we've picked up and that we can improve over time. So the first one is we should actually really understand the data requirements before, rather than as we go along learning. We should also do complete end-to-end testing before we do data exchange. Although everything we did worked, we want to be able to advance and improve as we go into the future. The database work, we should really, going into the future, agree everything up front and make time that there's time to work on both systems and that they're synchronised. And with any project, we should always add extra time for contingencies. Looking into the future, we actually see that this is something that can be replicated across all DNOs, so it could be a big benefit to everyone. The potential for a secure link to send control instructions between the SO and the DNO is really quite important, and it's also very, very robust. There is a potential change for some sort of form of industry codes to enable class to be implemented in a standard technical way, so that everyone implements it in exactly the same fashion. So let's think about the next steps. Both sides need to evaluate the long-term benefits from this link. What data will we have, and how can we learn from it? The learning from this project, we think, can be used to meet future challenges. So, as Simon mentioned, that networks are changing from being passive to active. So, is there something for a future DSO role that we'll need? We also think about the change to the generation mix and how much more embedded generation is going to be there. So can this sort of information help enhance our use of the system? And this real-time data sharing, it's placed ENW and the SO ahead of future anticipated EU network code changes. At the minute there's a change going through comitology, and this places us both ahead of the field. I'd like to hand over to Paul Turner now from ENW.
Hello, my name is Paul Turner and I'm the Delivery Manager for our innovation projects. I'm going to be today just giving you a basic system overview of the class system that we've set up. So from the project control point of view, we have a dashboard which enables you to activate functions from that dashboard, and that's carried out via in the GE Power and Fusion system. It also enables you to enable functions that will activate on site. That is linked to our network management system, which carries the activations across to the on-site substations. We have a link, as David said, ICCP Link, and that goes to a national grid. That enables the national grid control system to activate the other class functions as well. So in terms of on-site then, we have 60 primaries selected for the trial. At them 60 primaries, we have a device called an autonomous substation controller. This is a Siemens device, it's called the ASC in short, and what it does is that carries out the functions that come from the dashboard. So that will carry out the activations and or carry out the work on the actual dashboard, what the dashboard has asked for, and that is via the normal SCADA link. So today I'm going to be, there's various class functions. We have a peak lopping function which will save on sort of transformer reinforcement. There's a tap stagger function which looks at voltage control. We have a demand boost and demand reduction, but today in terms of trials I'm going to be talking about a primary frequency response. There's two types, there's a primary and there is a secondary as well. So the secondary frequency response is it's a slower response, and basically all that does is at 49.8 Hz, if the frequency falls below that level, all the 60 transformers in the trial will tap down by 5%. This will give us a voltage reduction, which in turn will give us a demand reduction, which will help support frequency. In terms of the primary frequency response, that looks at that's only actually on 10 of the class sites, so it only actually works on 10 sites. And what that does is you've got, also I should mention actually that all class sites we do have two sets of transformers feeding that primary. So what the primary response does is it opens the circuit breaker from one of the feeding transformers and transfers all the load across onto the transformer still in service. It does that without carrying out any tapping. So in effect, it's a very quick method of giving you a voltage reduction, which again will give you a demand reduction, which will again support the frequency. So for that response to be used by National Grid, that needs to be carried out within 1 or 2 seconds. Okay, so on the 17th of September at 2044, we had our first frequency event with the where we had the dashboard had enabled 6 sites. So if you can look at the graph, obviously it happened at 2044. You can see the dot that says 1. That is where the initial trip happened. Because you can see the frequency has reduced below that 49.7. So it's only actually done that on 2 sites, but you have to remember that this is the actual measuring. All sites did trip, and the Siemens device did see that the voltage level had fallen below the 49.7 hertz at all the sites. So it's purely in terms of slight errors due to the measuring equipment fitted. We've also highlighted at number 2 there's a slight peak, and again that's the same issue. It's down to the measurement scanning or sample rate, so it's not expected that that site did actually peak at 50 hertz. Okay then, so if we just look at one site, which is Fallowfield, the frequency was 49.9 hertz, and during the amount of time the frequency level gradually reduced, and as you can see from the voltage levels on the measurements, T11 and T12 transformer was sharing fairly equally. The voltage was between 6.6 and 6.5 kV. Again, the powers are fairly equally split between the 2 transformers. So we had the frequency response. The ASC opened up the circuit breaker. So you can now see that T11 has now been offloaded. So obviously the active and reactive powers are now 0, and you can see that the voltage level on that T11 transformer has increased to above 6.6 kV. On T12 transformer, you can now see that's picked up all the load, and actually the voltage level, as you'd expect, has decreased. So it's decreased to 6.4 kV. This has also made a decrease in the powers, so the power has actually decreased, the active and reactive power. Okay. So if we just look at a voltage graph then, so you can see T11 and T12, 0.1, you can see that's where one of the transformers tripped. So you can see that the T11 voltage increased and the T12 voltage decreased due to the fact it's picking up the load. If you look at 0.2, you can actually see the decrease, but then you can see a rise. It's like a step change. Now that's due to the fact that an on-load tap changer higher up in the system had tapped up the voltage. So that's why the voltage actually increased to a period of time. The Siemens ASC at 0.3 then looked at taking action to reduce the voltage level back down to the 5% level. So again, you can see at 3 that the voltage level has decreased. 0.4 is just showing the normal fluctuations as such that you get regarding the amount of demand you have on the network. So the voltage level is always changing. You're never going to have a smooth voltage curve, and that's what makes it quite awkward really for Manchester University to tell what actual response are you getting pre and post these trials. Okay, so again we've got a graph of the active demand. 0.4 again is where the trip happened, and you can see again the power levels are changing. There's quite a lot of oscillation there, and that's obviously due to changing demand levels, and you can see as well that there has been a decrease in the active demand. 0.2 and 3 again, you can see the step changes, the fact the voltage has increased, and again at 0.4 you can see where it's decreased again. Okay, so in terms of conclusions for Fallowfield then, the transformer tripped as expected, as it should do at 2044. A voltage reduction was seen of 1.44%. An active power reduction was seen as 2%, and reactive power was actually seen at 13.9%. So as I already explained, the voltage level did vary. There was a variation in voltage and power levels, and again that was due to on-load tap changes at a higher level, tapping the voltage up. And there are various power variations that are just part of a general network. So we actually have had 3 events, but these 2 tables are just showing 2 events. So the event I've just gone through at Fallowfield was the 17th of September, and that happened at 20:44. So as you can see the results there for Fallowfield, Hyndburn Road in Goulburn and Bagley. We don't have the change in power, or the change in active or reactive power for Hyndburn Road and Goulburn, due to the fact there was a lot of changes and oscillations there, so it's very hard to work out what the actual effect was. Again, if you look at, we also had a second event on the 15th of December at 22:43, and again this time we could actually tell what the changes were per the reactive and active powers, and you can again see that there was a voltage change. So in terms of looking between the 2 sites, so if you look at Goulburn, the voltage difference on the 17th of September was 3%, and on the December one, the actual percentage was a 2% reduction. Now that's purely down to the fact you've got different loads on at that time which have a different effect due to voltage reduction. And so in conclusion then, what we found is there's a voltage reductions really by about 0.88 and 3%. There's been a demand reduction between 0.84 and 2.67%, and this has been achieved by tripping a transformer. In terms of this work, there's a lot more work for the university to do to look at the effect of these, and we will be carrying out some more trials. So we'll be carrying out a lot more in-depth analysis on what actually we're expecting to receive. The first few trials I've shown, there are difficulties in assessing the impact of the voltage reduction and the tripping of the transformer, especially when you have sort of tap changes at higher levels, tapping and changing the voltage, and due to the fact you do have a varying load throughout the trial period. What we found is between the relationship, the initial outcome at the submission stage was we were expecting a 1% voltage reduction or increase would give us a 1% demand reduction or decrease. So I found that it actually varies really. So sometimes it could be less. A lot of times it's actually more. So the university work will be very important in looking at customer types, and also looking at that relationship throughout the year for every half an hour period, because then this work has shown that there's no set figure, so the relationship does change. So one of the important outcomes of the project will be that we will be able to map that relationship, and that'll be a very good output. Okay, if I just pass on to Simon Buck.
Okay, thank you to David and Paul for telling us more about the ICCP Link and some of the outputs of the trials that we've had. I just want to wrap up the presentations this afternoon just by talking about where we are going from now. The project closes at the end of September this year. We have the last phase of the trials. We're currently in the last phase of the trials and customer surveys at the moment, and then we move into the analysis, the full analysis that Paul spoke about being provided by the university. And then we get into the phase where we start to write up and put together the close down reports and hold the close down event. We have a number of dissemination opportunities over the last 3 months from July to September. But before that, we've got an SQSS workshop on the 10th of April, which is coming up, which if you don't know about, I'm sure we can make sure all that information's on our website, and you can join us if you wish. In July, we're going to hold a demonstration event of how the ASC actually works and how the links between the various pieces of equipment works. So we'll let you know about that, but that's going to be sometime in early July, and then there'll be a close down event for all our stakeholders to attend, which will provide the whole information on the project.